Can you hear me?
That's
Okay. Okay, I guess it's time to start. Welcome everyone to the second session of the afternoon. And here we have Henry, and he's an undergrad at Princeton University. He has joined work with Pratik, and now he's going to present his work on using BGP to acquire bogus TLS certificates.
Okay, so I'm from Princeton University, and over the last year, I've been doing some really interesting work, which actually ties a lot into our keynote that we just heard about using BGP attacks to get bogus TLS certificates. So let's just take a step back and motivate this problem. When I go to log into my login page at Princeton University, the login server is hosted at fed.princeton.edu, but I'm on somebody else's network. How do I know that I'm actually getting the correct server? Well, the answer is that they present their public key in a certificate, and the certificate has to be signed by a certificate authority that I trust. So we've heard a lot about certificate authorities, but just to demonstrate, here's the chain of trust. My browser trusts the certificate because Komodo signed it. And this is the way that even on first-time connections, going to sites that you've never been to before, you know that you can trust them. However, if we kind of take some steps back, we can realize that vulnerabilities in BGP actually allow an adversary to break this root of trust and have these trusted roots vouch for them, even though they're not the legitimate domain owner. So let's just take a look at how these certificates are signed. What process do they use to make sure that you actually control the domain? So if you want a certificate, you simply put in a certificate signing request containing the domain that you'd like the certificate for. And the certificate authority can't sign immediately. They have to come back with a challenge to show that you actually own the domain. So this is normally in the form of putting a document up on the root of your web server. And once you've performed those challenges, presuming that you actually own the domain, you let the certificate authority know that you did it. And then they go and check to make sure that that document's actually there. So they just send a web connection to perform that check. And then once they get the proper response, they give you your certificate. So it's a really simple protocol. But if we take a step back and look at this check, from an adversarial point of view, this is the only communication in the whole protocol that matters. Because you can be any client, ask for any domain you want. And as long as this check from the certificate authority to the domain goes through, you can get the certificate. So in the second half of this talk, we're going to look at simply ways that the adversary can intercept this check and fake the response. So sort of in another domain, how might an adversary do this? And it turns out BGP attacks actually provide a really good means of doing this. So this is a very simple network diagram. All of these are autonomous systems. And that's it's an entity in the BGP routing protocol. That's the backbone routing protocol for the internet. And they pretty much represent ISPs, internet service providers. And so here we have the certificate authority, the victim's domain, and the adversary. And in BGP, when the victim announces that they control a prefix of IP addresses, the routing protocol converges, and then traffic goes straight from the certificate authority to the victim. And the adversary, unless they're a major backbone provider and happen to be on this route already, they really can't get a fake certificate for you. But now, let's look at an attack that the adversary could perform. So if you announce a more specific prefix than the one that the original victim advertised, so importantly, this is a /24, meaning 24 bits of network mask, and that's more specific, containing 254 IP addresses, as opposed to the /23 up there. As a result, the adversary's route will be preferred by all of these routers because it's longer, more specific, and all the traffic will go to the adversary. So in this case, now, obviously, the adversary can forge this request because the traffic's going to go to them instead of the real victim and get a certificate. So it's a very straightforward attack. We see these on the internet quite often, but there's sort of a downside from an adversarial point of view, and that's that you're going to break connectivity to the victim. And that's not very stealthy. The victim's website's going to go down. All services running on that IP block will be affected. And even if you think you're a clever adversary and you try to, say, forward the traffic to the real victim, every AS on the internet believes that you're the real victim because you have the real destination because you have the more specific route. So if you try doing that, they'll actually just forward the traffic back to you. So unless this adversary has a tunnel right to the victim's ISP, which we can assume is very unlikely, there's no way to get the traffic to the victim to preserve connectivity. So this is a very noticeable attack. Somehow they still go unnoticed, but from a networking point of view, it's quite easy to detect these. Now, there's a black hat talk in 2015 that looked at a slightly more stealthy variant. And notice that I moved the certificate authority from up here to a little bit closer to the adversary. And that's because if the adversary announces an equal length prefix, so this is the same /23 prefix size as the victim, what they'll do is that they'll actually split internet traffic in half. So ASs that are closer to the adversary will prefer the adversary's announcements, and ASs closer to the victim will continue to route to the true victim. So if your certificate authority happens to be in your part of the internet, once again, you can get the certificate because it's in this affected region that's going to get routed to the adversary. And this increases stealthiness by a lot because ASs up here, not only will they not take this announcement, they won't even hear the announcement. It will never even propagate to them. So you can imagine trying to evade monitoring frameworks, evade the certificate authority from really noticing, let real users still going to the website. You get a lot more stealthiness with this attack, but in my opinion, the primary limitation here is that some adversaries just can't do it. And this is important to know because I think the adversarial model that we should consider is an adversary that's really one fixed, compromised AS. They don't really get to choose where on the internet they launch these attacks from. And if you're kind of at the bottom of the internet, far away from a lot of certificate authorities, this attack is pretty much useless to you. You're never going to capture enough traffic to get the certificate. So that brings me to the attack that our work's been focusing on, and that's this subprefix interception attack. So the idea behind this is that we go and we announce a more specific prefix, just like we did before, but instead of taking ownership of the prefix, we actually announce our legitimate route to get to that prefix. So we're just saying we can get to it through AS4. So to all these other routers, this is a more specific announcement, meaning that's going to be preferred over the more general one. However, AS4, in order to stop from importing a route that would have a loop, it's going to see that it has its own AS number in this announcement, and as a result, it's not going to import it. So to AS4, the proper route to 2222 is still the /23 that the victim announced. So as an adversary, all you have to do is put a forwarding rule in to say, well, if it's not from the certificate authority, I'm just going to forward it to the victim. But if it is, I'm going to answer it and get the certificate. So this is somewhat less stealthy at a control plane level, but I would argue that data plane is more important. And this has complete stealthiness as a data plane level, as you'll see in a moment. And once you perform this attack and you get the certificate, you're already routing the entire internet through you. So perfect time to start using the certificate to intercept connections. So what I want to do next is I want to show you how we actually perform these attacks. And some opening remarks before we do this. We control everything pretty much. The only real entity involved is Let's Encrypt, the certificate authority, and its real backbone routers that are making these announcements thanks to the peering framework in a very ethical way, compliant with their guidelines. But this is a real website out on the real internet. So as long as things go right, I just want to show my demo setup here. It's really small, but this is an HTTPS web page for d.ct2gt.tk, and it has the lock, so it's browser trusted secured. And it's also running an AJAX script going over HTTPS as well that's continually phoning home to the server and just sending potentially secret data. So this is an innocuous client that we didn't introduce in the last frame. And here I have some command terminals up for various entities here. This is the victim's terminal in blue. And this is, by the way, the victims in a network in Los Angeles. And we're just going to start packet sniffing on this. So if you look, we're listening to the packets, and you can see them coming in as the AJAX calls are going on. The two terminals down here are from the adversary's server, and it's going to make its announcements from Amsterdam, so really all the way across the world. And we're going to start packet sniffing on that. No packets, because the adversary hasn't made any announcements. And by the way, if there are any questions about the live demo, feel free to interrupt me. I want this to be sort of responsive and part of the Q&A time. And so right now, the adversary is not hearing anything, and that makes sense. So one more step before the adversary is going to go on, and that's that they're going to ask Let's Encrypt for a certificate. Okay, let me just make sure I type that. Sorry, I had these pre-typed, but then D is the right letter.
Serious props for the live demo, by the way.
Well, thank you. Hopefully it works. So let's hold the applause. OK. By the way, that IP address logging, you can actually perform this action from any IP address. So the final piece of the setup is to get this document right here. That's the verification document we have to upload to the web server. So I'm just going to copy that, take it out to another terminal I have open on the adversary, and just put that up on their web server. Should only, okay. Okay, so from the adversary's point of view right now, it's totally ready. And all I'm going to do now is make the routing announcement. So watch closely as the traffic from up here, if it works, starts being seen down there as well. Okay, it reconfigured correctly. And there we go. So what's happening here is that this is an interception attack, by the way. This is an interception attack. So the victim's still getting traffic. And this traffic looks exactly the same as before we launched the attack. Same source IPs and everything. But the traffic's now going through the adversary, too. And if you look closely at this packet trace, every packet's doubled up twice. And that's because the adversary sees it once on the way in, and where TCP dump's located, it sees it again on the way out. So that's how we know that we're intercepting traffic. But there's a rule in the adversary's route table so that if we hear traffic from Let's Encrypt, which until hopefully in a couple months just uses one fixed IP to do all their verification, it's going to perform the verification. So we wait for this, just one moment. And there we go. We get congratulated for getting a fake certificate. And the victim so far has seen completely nothing. To them, this is just normal traffic going about their day. And now all that we're going to do is actually use the fake certificate to begin intercepting traffic. OK, so now watch the web server output. And this is pretty much just going to restart the adversary's web server, let it start using the certificate. And there we go. So what's happened here is that the traffic was always going through the adversary ever since I made the announcement. But now that we got the certificate, the adversary can authoritatively answer that traffic. It can really pretend to be the web server. And as a result, these AJAX calls are no longer being answered by the victim. You can see its packet log is pretty much dried up. And they're actually all going to the adversary instead. But to the browser, this is still a totally secure connection. You can see the lockup there. And if we reload the page, we now got it copy from the adversary. And so it just changed certificates. The browser was looking at Let's Encrypt's. I used Let's Encrypt for both the certificates. They're really convenient. But it was looking at Let's Encrypt's certificate before. But I was looking at a certificate before with one public key. And then we just decided to change public keys on it. We didn't provide any explanation. But thanks to the partial implementation status of certificate pinning, browsers will accept this, and they really don't care, even though it just saw a different public key in the same browsing session.
The reason why people are laughing is because other people in the audience are going to your victim as well.
Oh, they are? Yeah. Oh, by the way, you might see some packets going in on this trace. That's because the nature of the interception attack, as you remember from before, some ASs are still routing to their real victim. So it's not going to completely disappear. So fortunately, that actually launched. And now we performed similar attacks. We actually went through and performed all 3 of the types of attacks I mentioned before. And we looked at 5 of the major CAs in the industry right now, and there really is no difference. Even though Let's Encrypt's the only one that overtly automates it, none of them require human interaction. They're all going to sign your certificate really quickly, and they're all vulnerable to this attack. None of them are using multiple vantage points yet, so Let's Encrypt could be the first. Yeah. And in terms of countermeasures, this is the main focus of our ongoing work. We like to look at this problem at the certificate authority level, just because there are way fewer of them, still a lot, but way fewer than trying to get adaptation of something by websites or clients. And we want to first force announcements to be totally globally visible, so no more local announcements. And this can be done by having multiple dispersed vantage points. It forces the adversary pretty much to announce a more specific prefix. And that makes their announcement really easy to see by network operators. So first we make the announcement visible. And then we want to actually give the network operators time to respond. Currently, BGP hijacks are handled sort of by social connections, you wake up, you notice there's a hijack, you call somebody who calls somebody who calls somebody. So we need time for that process to happen, and that's why we advise that certificate authorities implement BGP monitoring and only use routes that have been announced for longer than a threshold value. And we're running false positives and heuristics on that and trying to integrate with Let's Encrypt and Symantec to try to get their infrastructure to help us out. And we also have developed part of an open source solution. We're looking to further that. So I guess takeaways, if you're going to remember this, digital certificates are the foundation of our secure internet communications, but yet there are over 50,000 BGP-speaking routers, and pretty much almost any of them can perform one of these attacks to get a digital certificate for you. It happens in seconds. CAs will sign your certificate immediately, and then you can start intercepting connections from that moment before certificate transparency logs even notice the certificate. And we think that this is sort of a call to action to CAs to implement countermeasures and not just think about implementing countermeasures. And also, I think an important note is don't forget about routing security. Like, we think we're secure because we're pushing security up the stack to the application layer, but sometimes these application layer protocols are really not secure unless we have secure routing. So don't forget about BGPsec. And yeah, I guess I'll open the floor to questions.